All right, everyone. Welcome to the Calculus Summer Assignment Review. Um, I'll try to over-explain some things just in case, and really try to not only get you to answer the questions, but get that higher level of kind of where we're going in the calculus mindset. But the first one isn't too bad. We just need to find the equation of a line who's perpendicular to the line given and which passes through the point given. So the way we do that, well, we first need to remember how perpendicular and parallel lines interact with one another, or what they have in common, or how they're different. So a perpendicular line has a negative reciprocal slope to the line that it's perpendicular to. So if we have a given slope of 5 over 3, then the perpendicular slope is going to be the negative reciprocal. There we go. So that's the slope I'm using. So this is the slope of my perpendicular line that I want to find. And this perpendicular line that I want to find goes through that point. And this is where it's our first big calculus concept. We do not like writing lines in slope-intercept form. We prefer point-slope form. See, when we have point-slope form, as long as I have a point, an x and a y, and a slope, which I found because I needed the perpendicular slope, then I simply plug it into that formula. Now the general formula is y minus y1 equals m times x minus x1. So my x and my y are going in for x1 and y1. They're just kind of in opposite sections based on x, y, and y and x. And the perpendicular slope just fills in there because that's the slope that I needed to use. Now I do need to express in slope-intercept form, so again, the big calculus concept is learn how this form works, but any line can then be written in slope-intercept form by, in this case, simply distributing that negative 3/5. So I'm just going to write negative 3/5 x, distribute it to 7, and 7 is really 7 over 1, so I've got negative 3 times negative 7, which is positive 21, over 5 times the 1 on the bottom, which is 5. Now that's still not by itself yet. I now need to get it to say y equals something x plus something. So that just means I need to add 4. Now 4 with a common denominator of 5 is 20. So when I add 4 to 21 over 5, I'm really adding 20 over 5 to 21 over 5. So I get 41 over 5. So there's the line that's perpendicular to this line that passes through the point 7, 4. Hooray! Okay, now for the heady and abstract section of this guide, which is domain and range. Students typically don't like domain and range, but here is the idea at the end of the day. Domain simply means, is there any value of x that I can plug in? And you're going to see in most cases with most function types, any value of x is okay. We are allowed to square any number. We're allowed to square any number after we subtract it by 2, so the domain of this is actually negative infinity to infinity. We can plug in any number we want. That's just a way of writing anything from negative trillion, zillion, whatever, all the way to positive trillion, zillion, whatever, and every number in between. Pi, 0, 7, negative 25, everything's allowed to be plugged into here, and we can subtract 2, square it, and add 2 to it. Now the question then becomes, what y values will I get after I subtract 2, square, and add 2? And this is the big abstract idea we want to get in our heads. What happens when you square any sort of real number? Anything you're going to plug in? Well, what's going to happen when you square any number, if it's positive, it's going to become larger and still positive. If you square a negative, it's going to become positive and still larger by the same amount. But if you square 0, you're going to get 0. So if we think about that, that means when you square anything, you're either going to, or I should say, if you square any real number, you're going to end up with a either more positive number or 0. So what does that mean we can get for our range, for our y values? That means I can only get 0 plus 2 or any positive number plus 2, which means my range is 2. That's the lowest I can go, and we use a bracket because I will touch 2, all the way up to infinity, because I can always add a positive squared number to 2, but I can never go below 2. All right, so that's domain and range. So we use parentheses to denote something that you can't touch. So there's no touching infinity, or sometimes we'll use parentheses for asymptotes. And if we have a bracket, that means there's a hard cutoff where you can get this number. There's a way to get exactly 2 for my range, nothing below it, but I can also go as high as I want. How would I get 2 for my range? Well, I'd plug in 2 for x. If I plug in 2 for x, I'd be squaring 0, and I'd have 0 plus 2. So that is the lowest value this function will ever put out. One other connection, and this is another way to think about this, is if I graph this function. Graphs, things you should still be aware of when you think about this. You should be somewhere in the back of your mind as a calculus student saying, ooh, a positive quadratic in vertex form. That would be a wonderful thing to recognize when you see this. So what happens when you have a positive quadratic in vertex form? Well, that means the vertex is going to be found by, in this case, moving right 2. The x is kind of flipped from what you anticipate, and moving up 2. And any positive quadratic looks like this. Now, the reason I just want to graph this really quick is to show you the domain and range graphically as well. A quadratic goes left, 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 and up really fast, right, 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 and up really fast, but it goes left and right as far as you want. That's why the domain is negative infinity to infinity. The range, you can see there's this vertex point, and vertex point is, a mathy way of saying a very interesting point for some reason. That's not the technical definition, but that's what I'm going to say. And the reason we call it the vertex point is because the vertex point is where the range is cut off in a sense. In a quadratic, you can either go above the vertex point only if it's positive, or you can go below the vertex point only if it's negative. That's why the vertex is so important to find, because the vertex helps you determine where your range starts and stops, or rather where the cutoff for your range is. Okay, so think of all those ideas as you go through these questions. What can I plug in? What will I get out based on the operations happening? And if I know the graph, does that help me know the range any quicker? Absolute value graphs, just really quick, I'm going to do this kind of opposite, but no, I won't. I'll go the same order. What can I plug into an absolute value? Well, absolute values kind of do the same thing as squaring. If you plug in positives, you get positives in absolute value. If you get in negatives, you get positives in absolute value. If you plug in 0, you get 0 in absolute value. The thing is, you just don't change the value of the number. When you square 2, it becomes 4, but when you absolute value 2, it just is 2. When you square negative 2, you get positive 4, but when you square negative 2, you just get, when you absolute value negative 2, you just get 2. So the absolute value just says ignore the sign. So again, it's kind of related here. What happens when I find the domain here? Well, I can still plug in anything I want. And what will I get out? Well, same idea. I'll only get positives or 0 here, and then I'll be subtracting 7 from those numbers. So my range, in this case, will be bracket negative 7. That's the lowest I'll go, because the lowest I can be is negative 7 if I add 0. Or I can go higher because I can take negative 7 and add any positive value I want by plugging in any number except for 0 in the domain. Again, what does an absolute value graph look like? And then I'm actually going to stop graphing these. It would look like this. You'd go down 7. And because it's just a single positive 1x, it would have a perfectly diagonal slope of 1 over 1, and then it'd be reflected this way, which is why, again, these domain and ranges behave similarly, because they're both positive quadratics and positive absolute values. All right? I'm going to go through this a little bit more intensely now. A square root function, and algebraically rather, a square root function is not allowed to have any number plugged into it, or rather, a square root will not behave nicely with every type of number. A square root will only give you a nice answer or an output for the range if you're square rooting 0 or a positive value. You can't square root negatives because then you get imaginary values, and those won't count in terms of determining our domain and ranges. We want real values for domain and ranges. So how do we figure out the domain? Well, the domain here, here's one way of writing it, is anywhere that 3x minus 7 is greater than or equal to 0. Right? Because if 3x minus 7 is greater than or equal to 0, that's another way of saying that my domain is whatever's inside my square root is 0 or positive. Well, how can we write this in a different way to make it kind of look like this? Well, we can solve that, and we can solve that by adding 7 and dividing by 3. So now my domain is anywhere that x is greater than or equal to 7/3. So what's another way of writing that? Well, that's 7/3, comma, infinity. So that's going to be my domain. My domain is anywhere that x is 7/3 or larger, forever and ever and ever. What is my range? Now this is definitely a little bit more advanced. What does a square root function do when you square root it? Well, if you square root positives, which we can only square root positives, you're going to stay positive. If you square root 0, you're going to be 0. But then we're going to negate that and add 4. So what does that do in the grand scheme of things? Well, here's what happens. What we're really saying is we'll have 4, and we'll be subtracting some positive amount from it. So 4 minus 0, or 4 minus 1, or 4 minus 7, or 4 minus 85, or 4 minus 257, who knows what. So that means our range, and this is a little bit weird way of writing it, is negative infinity all the way to 4. So when we write our domains and ranges, we go from least to greatest. So my range can actually go down, down, down forever, because if I end up square rooting a trillion, I'll have negative the square root of a trillion plus 4, which will be a very negative number, and I can always go more and more negative. But the highest I'll ever go is when what's inside my square root is 0, because then I just have 4 minus 0. That's the largest I can go for my range. Moving more quickly and understanding more ideas about functions, this is a cubic polynomial. And I have no idea what this looks like particularly, but I know that any positive cubic, all right, positive in front, odd degree here, has this kind of behavior. It has some sort of shape like that. Now that already tells me my domain and range. My domain is negative infinity to infinity. And my range, if we look at that picture, which is definitely not accurate to this, but that's the idea of what a cubic looks like, is also negative infinity to infinity. So where am I getting this kind of picture from, or this idea from? Well, let's talk about it like this. Domain is what you're allowed to plug in. You can cube any number. You can square any number. You can multiply any number by 7, and you can take all that and subtract 8 from any number. So any number can be cubed, squared, multiplied, or subtracted from. That's what makes our domain work. There's technically some more stuff going on in there, but that's just a way of saying it. Again, we can square any number. We can absolute value any number. We just can't square root any number. That was our first problem we came into contact with. Now the range, again, you might think since it's like cubed, squared, x, it might behave like a quadratic where the range has a limit, but an odd polynomial, an odd degree polynomial, where the highest term is an odd, or the highest degree term is an odd number, is going to have this behavior where the range is negative infinity to infinity. Any odd polynomial has that behavior. Now sometimes it'll be flipped the other way if it leads with a negative, but that's still, again, some other stuff from Algebra 2. Up next, we want to find the domain of this only, because I said all ranges except for E. So this time we just want to find the domain. Now domain is what you're allowed to plug in, and this time there's just one thing to consider. But before we get to that, let's just think here. This is a rational function, a function that's made up of a ratio or a fraction. Now this fraction is made up by quadratics, and so one thing we learned to do in Algebra 2 and Pre-Cal is factor these. We can factor this to be x minus 4, x plus 1, and we can factor this to be x minus 9 on the bottom, x plus 1. And we would even cancel those. That would become a hole in our graph, which is super important. Holes are where limits come from, and we'll get there. But you might have already jumped ahead and you might make that connection now that a hole is that open circle in your limits questions that you interact with on graphs. But we end up with this. Now, again, then the question becomes, what am I allowed to plug in? That's all I need to know for this. Well, what are you allowed to plug in actually goes back to kind of here and here, not what cancels, because the hole is still there. Again, it's something we'll discuss more. But let's think about this denominator right here. If a denominator of a fraction is 0, then that is a big, big problem. We are not allowed to have 0 in our denominator. So what am I allowed to plug in? Anything that does not make my denominator 0. And so let's take a look at this right here. What would make my denominator 0? My denominator would be 0 if x was 9 or negative 1. So the denominator would equal 0 if x equals 9 or negative 1. That means our domain, here's the way we're going to write that, is negative infinity up to negative 1. So notice I'm using a parentheses now because I'm not allowed to be negative 1. That would make my denominator 0. I can be just up to it, parentheses, something I can't actually touch but be very close to. Again, that's technically the idea of a limit if you've worked ahead. Then I can be anything from negative 1 all the way up to 9. Notice I'm not going in order of how I found the roots. I'm going in order of least to greatest. Now again, I can't touch 9, and then anything on the other side of 9 all the way up to infinity. All right, that is my domain for this function. Again, notice that if you cancel out the hole and only base it off this, you're going to miss the fact that negative 1 is not allowed. But domain is based on the original expression, not the simplified expression. So that's a very technical note. And again, that simplified expression with this piece missing, that is what makes a hole in the graph, and we'll discuss that more in class. Just wanted to say that. This video is getting a little long, so I'm going to cut it off, but there's part 1.